Hello everyone, I'm Mahendrini from Construction Information Technology Laboratory. My presentation is about automated generation of geometric digital twins of existing rail infrastructure. I would like to start off by defining the digital twin. A digital twin is a digital replica of a real-world asset such as building, a bridge, railway or any other man-made asset. Digital twin is based on massive cumulative real-time real-world data measurements in multiple dimensions and uses this information of a digital model across the entire life cycle of the infrastructure. The fundamental feature of digital twins is its 3D geometry, without which many digital twin applications do not exist. So throughout this presentation, I am going to use the adjective geometric to highlight the digital twins with only geometric data. Moving on to the background of our project, the UK has the fastest growing railway network in the Europe. However, railways are complex safety critical systems which unfortunately face risk. Maintenance and safety management are therefore vital operations in the life cycle of existing rail infrastructure. But when we consider about European and UK rail industries, they are old and outdated and are becoming more difficult to maintain. For instance, the railway system in the UK is the oldest in the world and a patchwork of overlapping designs built at different times. Therefore, the current maintenance processes can no longer cope with the increasing complexity of these modern, complex socio-technical systems due to the absence of digital representation of old railways. Therefore, the objective of our project is to devise, implement, and benchmark the performance of a framework which generates geometric digital twins of rail infrastructure from airborne LiDAR data. Our proposed framework contains three phases. It starts with raw railway point cloud data. The detection of mass prior to other railway elements is quite important because it can provide the relative position layout for the rest of the rail assets. Therefore, in the first phase, we automatically align the railway dataset from its arbitrary orientation. And next, we remove vegetation and detect and reconstruct railway mast as IFC objects. For the next two phases, the input dataset is the narrowed railway point cloud along with the mast position coordinates. Each of these phases detects and reconstructs the geometry of overhead line equipment and track structure elements. We have analyzed the existing fault detection methods not only for the rail infrastructure but also considering road networks. From the background study we carried out, we could see that there are specific limitations exist. To name a few, mast and other pole-like object detection methods usually depend on the scanner profile information, and majority of these methods does not provide automated solutions for the detection procedure. Therefore, we conclude that there is no solid approach to detect railway mast automatically from airborne LiDAR data by satisfying all user requirements. So we have derived our research objectives for this phase as given on this slide. Point cloud is given an arbitrary position and orientation. So we first needed to align the course of the railway parallel to the global axes in advance, as all features to be extracted in further steps lie in a global coordinate frame. Therefore, we first align the rail track by chopping the whole dataset perpendicular to its principal direction. That step was also needed to remove the vegetation from each of these small units. Once all the noise points are removed, the only vertical element parallel to the z-axis should ideally be mast. So we used a line detection method to detect mast as lines. However, as there were few other remain tree trunks and few vertical objects close to the rail track, these detection results were not sufficient enough to extract mast as point clusters. So we followed two refinement methods to sort mass from other pole-like objects. First, we took the top-down point densities to sort mast from tree trunks as given on the step 3. This is the ideal point distribution around a mast and a tree. So when we get the density ratios as a threshold to sort mast, we could filter most of the masts from trees. To increase the accuracy, then we used a next refinement algorithm which took the railway topology knowledge so that it could search mast pairs along the regions along the rail track where we could positively expect masts. We produced the final model of the mast using implicit representation of an I-section by considering resulting positional coordinates and lengths of each point cluster. For the next phase, according to the background study, the complexity of overhead elements, including data gaps in the cables, vegetation, and bundle cables, reduce the accuracy of the results of existing detection methods. And many of the methods are sensitive to voxel size, threshold settings, and point density. And few studies overlook the sagging of the cables, while others assume cables are series of small straight line segments and that cables are always parallel. Overhead elements are very thin, therefore often represented with few or no points. The detection of overhead elements is difficult due to this presence of vegetation as well. So these factors make the methods mentioned for the detection unproductive. So we set our research objectives as given on this slide to fill the gaps in the research. We used the resulting aligned and narrowed railway point clouds and mass position coordinates of our previous step as the input data for this method. So first step, in our proposed method, we automatically extracted the point clusters of the overhead elements described at the beginning. This unit is hereinafter known as C-section. So we used a crop box filter to extract point segments of the C-section. This filter automatically extracts all the data within a given cube in 3D space by removing any points that do not satisfy the given parameters of the cube. Secondly, we extracted the point clusters of cables using Ransack algorithm, which consisted of two refinement algorithms to improve the accuracy. These refinement algorithms first divided the whole point cloud dataset into near straight pieces and then removed the ground plane and finally upsampled the points on the cables to reduce the computational cost and increase the detection accuracy. As the next step, we generated different configuration of parametric models of overhead system elements, which represents all existing overhead system configurations in the Europe and UK. Our algorithm automatically converts these models into points. So now we have two different configurations in PCD format. The algorithm then uses iterative closest point algorithm to find the most suited configuration and the best possible fit. This finally produces the transformation matrices that provides the rotation and translation related to each C-section and the cables. Applying this to original IFC model, we could finally generate the geometric digital twin of the model as a one system. As explained earlier for other rail elements, the state of the research related to track structure have many limitations as explained on this slide. So we have set out our research objectives as automatically detecting railway track structure elements from airborne LiDAR data with varying horizontal and vertical elevation and complex railway geometries. And the second objective is to automatically separate rails from other linear elements close to the railway corridor without relying on prior knowledge such as scanning geometry. Simulator phase 2, we use the resulting aligned and narrow railway point cloud and mass position coordinates of our previous phase as the input data for this method. Initially, the method uses the Ransack plane detection algorithm to extract point clusters of horizontal and quasi-horizontal ground planes. A pre-processing step is used before the Ransack algorithm that divides the whole point cloud dataset into sub-boxes which approximate lengths or around 60 meters. We hypothesize that the only linear element on a sub-box now represents rails while the rest of the sub-box represent the trackbed. Next, the method detects rails using Ransack as lines parallel to track direction with an additional radius neighborhood search to include any missing points during the Ransack detection. To improve the results of the methods, we used a point-based calculation method to differentiate point clusters of rails from other linear elements and lines on grounds. So this method generates a parametric model of different rail profiles and trackbed profiles as the next step, which possibly represent the all different geometries that exist in UK and Europe railways, following the procedure explained in the previous slide. So the method uses the same convergence procedure explained previously to automatically select the optimum rail or trackbed profile and to converge this model to previously detected point clusters, and we finally merge all produced IFC objects together to build the final model of the track structure. We measured the detection accuracy comparing the automatically extracted point clusters against the ground truth data using performance matrices. The evaluation process chose distance-based cloud-to-cloud matrices to evaluate the automated twins by comparing the twinning quality between the ground truth data and automated ones. Now, the problem of comparison of twinning quality is transformed into measuring the difference between the two sets of point clouds. The final accuracy was of over 90% F1 scores for all railway elements, and the average modeling distance between ground truth and automated was less than 5 centimeters. Moving on to the conclusions, our framework is a novel automated model-driven method that exploits the highly regulated and standardized nature of railways to generate geometric digital twin rail infrastructure. And this method can deal with real railway point clouds, consist of varying track slopes, curvatures, and also effective in handling challenges inherited in point clouds, such as occlusions, extreme vegetation around the railway elements, and local variable densities of points. Also, our method still provided high detection rates and can correctly represent the geometry of railway elements despite the different geometries appears on the tracks such as overbridges and tunnels. And also this method offers significant computational cost reduction by automatically cropping a lengthy railway point cloud into relatively straight segments. This enables a considerably improved large-scale object detection generally required over kilometers without forfeiting precision and manual cost. Therefore, this is the first method to automatically solve the generation of geometric digital twins of existing rail infrastructure from railway point cloud data by exploiting repeating railway geometric patterns which lengths over kilometers of spans without needing any prior information. And that's the end of my presentation. I would like to thank Fibro who provided data for evaluation. This research is funded by Cambridge Trust and Bentley Systems. I gratefully acknowledge their support and thank you very much for your attention.